All right, welcome everyone. Thanks for inviting me. I'm Zoltan Nagy. I'm faculty at the University of Texas at Austin. I will first of all thanks the organizers to invite this great workshop and symposium, and I had a lot of fun listening yesterday and then this morning. And then I'll see if I can keep the level and also pick up on the time. So we'll see. So my title is about CityDNN, and before I get there, I want to just give a shout out to my group and point out a few things that have been said a little bit over the last couple of days or last days. Is that this topic of using machine learning in energy systems is interdisciplinary by nature, and so ideally you would want people at the table in a group that are coming from different backgrounds, and so I we try a lot to do that. And so all of these people you see here, a mix of undergrad and grads, but also a mix of from CS to architecture and everything in between, which is pretty cool. And the project I'm showing you today is in fact one of those projects that are unfunded, and people just kind of think around with an idea, and then all of a sudden it becomes pretty cool, and then maybe goes somewhere later on with people from different backgrounds. So before I get there, it's an idea what kind of like the group's working on in general. Intelligent Environments Lab, it's really all topics around these energy systems, combining machine learning, building energy. A big topic, I don't know if you can see my mouse, but a big topic in the top right, reinforcement learning, which Mario introduced beautifully this morning. In fact, Mario and I organized a workshop just 2 or 3 weeks ago at BuildSys, with the topic of reinforcement learning and building energy management and urban energy management systems. So if you're interested, I put the link into the chat. We had about 100 participants, also from all over the world and all over, national labs and universities, because it's a pretty cool topic coming soon. And so we are trying to build a community around that and trying to standardize processes, standardize problems, and also define the big problems, and a few of which we have started discussing this morning. Another event that I'm organizing with Dr. Henze, who I think is in the audience from CU Boulder, is the CityLearn Challenge, which is dealing with reinforcement learning in an urban context and trying to come up with ways to, coordinate the energy use between buildings so that the response of the whole environment or microgrid, and that can be 10, 20, 50, 100 buildings, is reducing the peaks, reducing the duck curves that we have seen early on. And some of our earlier work, and that we also published, is showing that you can get quite nice shifts, but you do need storage. And so that becomes an interesting question of who pays for the storage when it's locally installed, but the benefits are reaped on a social level or on a societal level. And so a lot of interesting questions. If you're interested, we will be organizing a new one this year. We're working out the details. We will have monetary, compensation for the top groups. So we're looking forward to many participants. Shoot me an email or follow me everywhere, and then you can get informed. So today I want to talk a little bit about about our work on supervised learning and talk about this deep neural network that we developed. But before I give you I want to motivate it a little bit, because before I get to the technical work. And the numbers, a lot. The built environment is responsible for a large amount of greenhouse gas emissions. The good news is, combined in terms of generation, distribution, and store and end use, there's also big potential to reduce these greenhouse gas emissions. And so we just, and also the technology is really there, so we just have to do it. So one thing that we need to remember, or that I try to emphasize when I talk about this, is that we need to play the long game. But the long game, when you hear these, we need to be carbon net zero by 2050 or whatever the other year is, we need to remember that energy systems and buildings and HVAC systems and buildings have a lifespan. And so if you're talking about 2050 and you start working back, then it means pretty soon that every single building you build today, you retrofit today, you design today, you update today, will be part of that building stock in 2050 that needs to achieve that goal. It's not going to be a switch at 2049 that all of a sudden every building will be turning carbon neutral. And so that's just something to remember. Like it's a long game, and we need to think in time spans now, because over time things are getting worse. And that's kind of like the theme of the talk as well, a little bit. The challenges that are coming with that, when you think about long terms, is that we have things change slowly. If you add new technology, it's not going immediately into market. That has market issues, policy issues, and things like that. But there are also things you cannot influence, and you kind of have to, work with them. Climate change is one of them. So estimating energy use today with the weather files we have today is we're not going to do much for 10, 20, 50 years estimating that. But on top of that, you have, development of the urban environment, population growth or degrowth, and all of those things kind of like need to be considered at the same time if you want to make projections in the future. And so I highlighted those three topics because those are the ones that I want to focus on in terms of motivation and what we're trying to address. I also want to give a quick shout out to the motivative work, which is Dr. Falconer's work, who is having a lightning talk later on. So you get a little bit of a sneak now. And because we worked off of this problem for that. And so what you see here on the left-hand side is West Campus area here in Austin. And we can run a simulation model, urban energy model that takes into account all these different types of buildings and forecast the energy use. But we wanted to take a little bit further because, like I said, if you do that for 50 years, things would change. And so, what if? And here you see a small part, which is the green part at the bottom, which is currently only single-family homes. But if you took that part and then started to redevelop it, and redevelop it with, low-rise buildings for a while, then mid-rise buildings later on, and then maybe high-rise buildings at some point to, allow for more densification, allow more and more population, or to, allow for the increase in population to be taken up by the neighborhood that we kind of expect in this area, or one population growth scenario might expect, right? And so if you do that, and the colors on the background kind of give you an idea of the fraction of these different types of buildings that we would need to have in this very quick, very rapid development in order to be able to, for a given population growth, to pick up all that population. But I want you to focus on the two, the dashed line at the bottom, and then the solid line. One of the lines, the bottom one, is what happens to that area in terms of energy use if you keep the energy, the weather file constant. So we assume the weather is not going to change in patterns, and it's the same that has been, the same the past 30 years. We use a TMY file, what it's called for Austin. And so the increase you see there is the increase in what would happen if just the population increases, the buildings increase, and so on. And it's per square foot per year kilo energy use. But then the other line on top of that is what happens when that effect is exacerbated by increasing the energy use due to warmer and warmer climates. And you can see the details in Dr. Falconer's talk, but you can see from that slide already, or from that chart, that by 2050 we expect an increase in energy use solely due to climate change. The horizontal, the dashed line is not that big, but the other one is increasing quite a bit. And this is, this is knowledge that you need to have when you're starting to do things like, what kind of retrofit scenario should we incentivize? What kind of buildings should be built? How should we develop the building code? What kind of goals should we set ourselves? What kind of target should we set ourselves? What is the utility going to need to build to address this kind of change on a very local scale for a municipality, right? A large, like 1 million people or so around the city. And so with these questions, because it's in the future, obviously we cannot predict, right? What we can do is we can run a bunch of simulations. But the problem is when you start doing these simulations, obviously, you need a lot of them with a lot of these buildings. And so it's going to take time. And ironically, running them on computers, time takes energy and also contributes to greenhouse gas emissions. But so the point is we need something that can create these scenarios quickly and in a way that we can assess them. And because the not much changes, our approach is to say, well, we use a simulator called CitySim, which gives us the urban energy model for given inputs. And so what we thought to do here was to basically pre-generate a lot of these scenes and run basically an exhaustive search of variables that can be used in these models and pre-compute those. And then when we want to run the scenarios, or when somebody wants to run the scenarios, we just run the DNN, the neural network. And so basically we're just trying to map the simulator, which goes into physics and does ray tracing to account for, what buildings are seeing each other in terms of shadowing and things like that. And so just abstract it out and try to take all that knowledge and squeeze it into a neural network and see how far we could get. And that's how they started. So we took these models. There's a lot of scenes. Some are more low-rise, some are more high-rise, some more mid-rise, and then we put them into different climate zones because, again, we want to generalize. So we looked at all over the country, so to get a good sampling for that. And then we also randomized the non-geometric properties like U values, building construction, and window-to-wall ratios, and things like that for the buildings, and then input it to weather. And then so what we get out of that is, solar gains and thermal losses, which are not energy in itself, because on top of that, you would need the actual systems, but it gives it a contribution of the built environment. And so you can start doing scenarios, what the built environment itself would demand for heating and cooling loads. And so, we took all of these data points, we simulated everything, and in the end, it's, hourly simulations of like 2,500 buildings in so many different settings, and so each of those buildings generates an annual energy use or solar gain and thermal losses variable for every hour for all these given parameters, and then we use that to train the neural network. And this is just an example. The network, this is not the structure of the network, it's an example of that. And then, overall, I think 17 million data points that we used. Again, somebody mentioned before, if that's big or not, I don't know. That's a number that we used here. To give you an idea and to also re-emphasize what has been said before, you can do a lot with machine learning, but you cannot do anything if you don't incorporate any of the knowledge of what matters, like so like domain knowledge. So we know what will matter in terms of solar gains, we know what will matter for thermal losses in buildings, and so we use those variables. There's no sense of using other variables. So again, domain knowledge cannot be decoupled from the application of the machine learning algorithms. Otherwise, you get garbage, or at least not as good as you could get. And so here's the results. In a good approach, what we did was basically to simulate another set of buildings in another climate, and to basically get an idea of the generalizability of the networks. And so we get on both thermal and solar gains about 85% accuracy in forecasting. You can see here an example of over a couple of days left the thermal losses, and right neural network, the solar gains. In blue, the values we're looking to replace, and in orange, what we're getting. You see it's not perfect, but 85% for one is not a bad thing. But the real kicker comes when we compare the simulation times, which is when you run these models on CitySim, and for one particular task, it takes us 8 hours to run the model on the same PC. But then, of course, once you simulated it with the DNN, or once you have the DNN, you can run it in about 10 seconds. And that's major, because now 10 seconds running, hundreds of parameters is actually, or hundreds of sort of like scenarios moving forward, which each of them takes a new weather file. Each of them may take new buildings, and so you need to update those things as you move forward. And so you rerun those simulations. So running it in under 15 seconds, it's pretty cool. So with that, we can move forward. And I was going to stop here yesterday when I was preparing this simulation, and then I saw Kyle's presentation. It was talking about remote sensing and looking at images from the top, and I thought I'm going to throw in our like unfinished but like sort of like a thought for food process, because or current work, because there's one thing about buildings and the urban environment, which is you need to understand how they are with respect to each other. We know whether you're close to a big building, whether there's a lot of trees that may be shadowing and reducing cooling loads, and at least in hot climates. And so the things that we would like to have eventually is we'll take an image, and this is from Google Earth, and run it and somehow make it palatable for CityDNN and get then the energy demand out of it by just looking at the image. And so the current approach we're taking is take that image, augment it with data that we may have, so we should use, which is, city has oftentimes GIS data available on building footprints, maybe on some kind of tree inventory, which Austin happens to have. And so we can take that information, there's building heights, there's tree heights and things like that, and we can use that to augment the image. We can do some analysis on the image to understand orientation of the building, because that's important for the energy use. And then we run it, through the 3D model for CitySim, and we'll recreate the process that I just mentioned. But then what happens is we would also use the image as an input to that neural network, because the image actually contains building height. So these colors now that are color-coded are buildings with a certain height. And so in that image, there is an information now, what is around that particular building in the middle, for which we will try to understand the energy demand. And so with this, and together with, being integrated into a GIS system with the very quick computation time, what it means is that you can give this to, city planners, whatever, who already work in GIS, who can just use the CityDNN as a plugin and understand what eventual impacts their decisions, to zone a particular area or allow certain heights in buildings in certain areas might have 50 years down the road. And so that's pretty cool, we think. And so we're trying to, work further on this topic. And so I wanted to put this out here because it seems like a lot of people are working on this, looking at images. So maybe it sparks some conversations afterwards. And with that, I will say thank you again for the organizers. Thanks to my team.
Do you have the building height information already, or is that estimated from your model?
Excellent. So there are two answers to that. One, we use GIS information that has the building height, so that we overlay. So it's fusing the GIS data from the city with the image. So we need to find where that is. But of course, if you can estimate it from the image, which I also recently yesterday I saw some papers going around, if you can do that, that's another way to augment it and find it. So definitely, we're looking at using as much data as is available for the purposes. Remember, the purpose is to do it as a municipality type support for decision making. So oftentimes they do have some information.
Another question that came in is asking what open databases are available to integrate.
Yeah, that's always the $1 million question, $10 million question. Data, some cities are better with their open data initiatives and providing the data for free. Some you have to ask and be very persistent. Some will make you pay for it. It depends a little bit where you are. Same with utilities. There's two philosophies. One thing, data is common good and share it for free. Other things, data is the new oil and we have to monetize it somehow, and it depends where you are.
Right. Good answer. Thank you again, Zoltan. That was super interesting.